Here are some points in 3 dimensions, and what I want to look at is what UMAP is going to do with these points. So let's square them up to start with. Now this is what UMAP does. So you can see it's done a nice job of separating the clusters, but also we've lost some information. So the clusters were spread out to different degrees, but in the UMAP view, the size of the clusters more reflects just the number of points in the clusters. And in particular, this cluster here, if we look at the original data, it was really spread out. We've lost that information. But it really has done a great job of separating the data into clusters. There's clusters inside other clusters here, and it has managed to separate them very nicely. I'll also show you the t-SNE. t-SNE with suitable parameters produces very similar results. So some good, but we've also lost something. Okay, here's another example. So we have 2 sort of structures that parallel each other. Maybe this is from an experiment with some sort of treatment. And as it happens, there's less points in one of these structures. So let's square it up. Then the UMAP. Again, we have the size of the clusters reflecting the number of points. And we've lost the relationship between the clusters. And then the t-SNE, we've completely lost the relationship between the clusters. And you'll also notice it's sort of made a bent what was originally straight. It's made the data look kind of biological where really it wasn't. But it has preserved the topology of the data, which is what UMAP and t-SNE set out to do. It's working as intended. It's just hasn't preserved a thing that we might be interested in. Okay, here's another example. 3 clusters, and they happen to be sort of really spread out in one of the directions. So let's square that up. Whoop. Now what will UMAP do to it, do you think? Well, again, it's gotten rid of differences in density, so we get this rather nice shape. And then something interesting has happened with these 2 clusters that were next to each other. They've actually joined together. So if we go back to the original view, you can see that that joined bit is where the points get spread out. In fact, points say in this cluster, they're near points in the other cluster, maybe to a similar degree to points that are in this cluster. UMAP and t-SNE are based on Euclidean distance, and so it starts seeing these spread out bits as linked together. And so I'll show you the t-SNE as well. The result is rather similar. So potentially misleading there if you have skewed data. Okay, another example. We have a sort of square thumbtack type thing. And so this is not something we can represent in 2 dimensions and maintain the topology. These methods aim to retain the topology of the data, but that's not always possible. So let's see what they do. So it tears off the pin from this thumbtack. So it separated something that was actually attached. The t-SNE has done something quite similar. So this can happen if there isn't a good 2D layout, or maybe these algorithms, they just don't find a good layout, and so they end up tearing apart things that should be connected. So that's something that can happen. But finally, here is a complex high-dimensional object, but as it happens, it is something that we can represent in 2 dimensions and preserve the topology of the data. So we could look at this spinning randomly in high dimensions, and you'll eventually make some sort of sense of it. But if we look at the UMAP provides a really nice map of the topology of the data. And so this is a good reason for using UMAP. So for example, we use UMAP in single-cell RNA-Seq data because it can show this sort of structure, which it might be a developmental set of developmental trajectories for some cells. And again, t-SNE, if you choose the right settings, performs similarly.